everybody. Today we're going to be taking a look at the 7.2 notes. This is over two different formulas that we will be using in this chapter. It's the exponential growth and decay formula and the compound interest formula. So first we're going to take a look at exponential growth and decay. That's what this formula is called. The way it looks is like this. So before we do an example with this formula, let's define what all of these variables mean. So starting with your y, that's your final amount. A, that's your initial amount. R is your rate of growth or decay. T is your time period. And normally that time period will be expressed in years. So we'll go ahead and make a note of that. All right, so here's our first example. In 1996, there were 2,573 computer viruses and other computer security incidents. During the next 17 years, the number of incidents increased by about 92% each year. So for part A, we need to write an equation that models the situation. So that's what we're going to do first. So we're going to use that exponential growth and decay formula to plug in some numbers, and then in part B, we're going to solve it. So part A is going to look like this. So we are trying to solve for the final amount of computer viruses. So we're going to leave y as y. Then, before we fill out the rest of this formula, we need to define all of our variables. So we just talked about y. Y was the final amount of viruses. We don't know that, so we're just going to write that out in words. But for the rest of these, we're going to plug in numbers for this. So for A, that's our initial amount. We've been told how many initial computer viruses there were. It's 2,573. R is the rate of growth or decay. So something to keep an eye on for R, whatever your percentage is in your example or your word problem, that is going to be your rate of growth or decay. So I just highlighted that 92%. Now the way we write R is very important. You must write R as a decimal. So we don't want to write R as 92. If we write R as 92, we're going to get a completely wrong number in our calculations. So we have to take 92% and turn it into a decimal. Easiest way to do that is to take the percentage, divide it by 100. That will give us our decimal. Now, that 92%, that R, it is increasing. We were told that our percentage is increasing by 92%. So what that means is that's going to tell us what sign to use in our formula. So see how the formula has a plus or a minus? That means we have to figure out, are we talking about exponential growth or are we talking about exponential decay? Now in this case, since we're increasing by 92%, I'm going to use plus. So let's make a note of that over here. So when we're talking about growth or increasing, we're going to use plus for R. If we're decreasing or decaying, we're going to use minus for R. In this case, we're going to use plus because we're increasing. Lastly, we need T. So what is the time period that this example problem is taking place over? Now, you're looking for the number that has the years attached to it. So that is going to be 17. Now, another way I could have gotten that is by taking the final year that we were tracking computer viruses, which is 2013, and the initial year that we started, 1996. Same thing. I can take 2013 minus 1996, and that would give me 17 as well. So finally, we can do part A. So I'm actually going to erase this here so you can see it better. So here's what our formula is going to look like. It's going to be y equals 1 plus 0.92 raised to the 17. So for part B, we're just going to answer that. We're going to take that 1 plus 0.92 raised to the 17. And the best way to do this is use your TI-84 calculator. This is just plug in the numbers, throw it in the calculator, press enter, and we'll see what we get. So let me move this a little bit here. So what we have to do is we have to do so based off of our formula, see, sometimes even I make mistakes. We have to plug in our initial amount first. So that is 2,573 to the 1 plus 0.92 raised to the 17. See how I forgot the initial amount? I forgot the A. It happens, but now we fixed it. So let's go ahead and plug the formula in correctly now. So we have 2,573 parenthesis 1 plus 0.92 parenthesis, and then remember to get your exponent, it is that little up arrow button just above the division button. So it's here. I need 17 for the exponent. Now I can press enter. So as you can see, since this is exponential growth occurs very rapidly when we're talking about exponential models. So what this is here, so it's going to be, how many numbers is that? That's 1, 2, 3, 4, 5, 6, 7, 8, 9. So that means about 168 million computer viruses are going to occur in 2013 based on this exponential growth model. So that would be 1684. 84779. 0.6 viruses. That's a lot. And that is because exponential growth is very, very rapid growth. The more years you have, the more you're going to grow, and it's going to go just crazy, especially over a 17-year period. Let's try another one. So here is a, very real world applicable example. In this example, we're talking about the value of a car. So it says the value of a vehicle in 2008 was $8,000. So that was the price of the car being bought from the dealership. The vehicle's value depreciates. Depreciates is another word for decreases at a rate of 12.5% per year. This is very true. When you buy a car, as soon as you drive that car off a dealership lot, it is going to decrease in value. And with each passing year, the car is going to decrease in value. So when you go and try to sell your car in a couple of years, when you want to buy a new one, that car is not going to be worth near the amount that you bought it for. Cars are a depreciating asset. So again, we need to write an equation to represent this situation. So that's what we're going to do first. We need a y, we need an a, we need an r, we need a t. So y is the thing we're trying to find. because in part B it says estimate the value of the vehicle in the year 2015. So Y is the thing we're solving for. So this is going to be the final price of car. A is going to be our initial amount for the car. So that's going to be our $8,000. R is going to be our rate of growth or decay. Now in this case, our car value is depreciating, so it's going to decrease. So what I have to do is I have to take my percentage, 12.5, and divide it by 100. And that's going to give me 0.125. You could do a calculator for this too. See, 0.125. Now, because we are depreciating, I have to use a negative for this percentage. We are depreciating at 12.5%. Now, for our time period, we know the price of the vehicle in 2008 was $8,000, and then we are going to estimate the price in the year 2015. So to find that time period from 2008 to 2015, I'm just going to subtract 2015 minus 2008. That will give me 7. So here's what our formula is going to look like. Y equals our initial amount, 8,000, parentheses, 1 minus 0.125, all raised to the 7th. So for part B, we're going to take that formula, we're going to solve it, get our answer. So here's part B. This is where you use your calculator. So that would be 8,000, 1 minus 0.125, raised to the 7th. So as you can see, exponential decay is no joke. It will go down in value quite a lot, and this is true for a car. So if you bought a car at $8,000, it's probably going to be worth about $3,000 in only 7 years. So we said our car is going to be $3,141. And then since we're talking about money here, we're going to use 2 decimal points because that's our cents. So 0.56, well, the number after 6 is that number. So we're going to round the 5.6 up to 5.7. Part C, we're going to skip. We'll learn about that later on. Next example. This is on the back page. So this is the other formula that we're going to talk about. This is compound interest. So here is your formula for compound interest. Let's define these variables. In this case, A is capital, and A means final amount. P is something called the principal. This is the initial amount. R is your rate of growth. And we write it as a decimal. Now, with compound interest, our R will only be growing because this formula is used when talking about investing money. So think about it. If you have some money and you want to take it to a bank and invest it and have your money grow with compound interest over time, would you go to a bank that offered a growth rate that was negative? Like, why would you go to a bank and put your money in the bank and then have your money decrease in value over time. No one's ever going to do that. So that's why R will always be positive. And then T is also the time period. And that's going to be in years. And then there's one more letter that we've not talked about yet, and this is N. So this is going to be the number of times the interest is compounded in a year. So we'll do an example and we'll talk about what N means. So with compound interest, your money is not going to just increase like once a year. It may increase multiple times in a year. So it's going to take the money that you're earning with interest, and then whatever that amount is will get compounded into the next time the interest rate is applied to your initial investment. So you will see in a second what I mean by that. So what we have here is we're going to do 4 examples. So what I want you to do with your paper here, I'm actually going to zoom out a little bit so we can see better. I want you to take your paper and I want you to divide it into 4 quadrants. Not my best straight lines. Let's try that again. So we have 4 quadrants. So we're going to do one problem for each quadrant. So we're going to do A, B, C, D. So what this is we are going to find the balance of our money. So we have $4,000 as a class. Let's say we're taking this money, we've pooled it all together, and we're going to take it to a bank. And most banks do offer what's called a compounding interest rate, where if you give your money to them, they will hang on to it for you. And if your money just sits in there with the bank, it will increase over time at a certain rate. So we're going to find what our final amount of money is. If we have $4,000, it's compounding with a 2.92% interest, and then that interest is going to compound a certain amount of times during 1 year. So let's define our variables over here. So we have an A, capital A, we have a capital P, we have an R, we have an N, we have a T. So for A, our final amount, well, that's going to be how much money we have at the end of our time period. So our time period is 3 years. Now P, that's our principal. So that just means, well, how much money are we starting with? We're starting with $4,000. R is 2.92%. Now the way we find R, you have to take 2.92 and divide it by 100. Now you're going to see when we do that, we get 0.0292. That's 2.92% right there. What I often see people do is when you're dividing like a single digit interest number, like 2 or 3 or 5, they want to write it as 0.5 instead of 0.05. That is a very common mistake. Make sure you don't do that. So we have to write our R value like this, 0.0292. Now for the N, I'm actually going to leave the N blank because we're going to do 4 different examples where the N value changes. So how many times is our interest getting compounded in a year? So here are all the different N values that you may run into with these kinds of problems. So the first one, A, that's annually. Annually means once a year. Think about like if you have an annual flower, that flower is going to bloom 1 time a year. Quarterly, think about, well, how many quarters are there in the school year? That's going to be 4. I don't know why that went to purple. Let's change that back to red. Monthly, think about how many months there are in a year. That's 12. Daily, how many times is it going to compound in a year? Well, how many days are there in a year? 365. So what we're going to do is we're going to write out all these different formulas using this formula up here. Now, the only thing that's changing with each example is that n value, how many times we're compounding. So here we go. We have A. I'm going to do A with annually. So that's going to be so our principal in this case is 4,000. 1 plus R over N. So it would be 0.0292 over, in this case, our N value, we're compounding just once. And then for our exponent, we have to take N times T. So that's going to be 1 times 3. So let's go ahead and plug that in our calculator. So 4,000 first, then a parenthesis, 1 plus, now we need to use our fraction key. If you remember how to use that, it's alpha y equals, enter. So this is 0.0292 over 1. Close the parenthesis, and then hit your exponent button, and then we need to do n times t. Then we press enter. So after 3 years, it looks like we gained about $360. That's pretty good. So it's $4,360.73. Now that you've seen how one of these formulas works, go ahead and see if you can do B, C, and D on your own. So if you want to pause the video at this point, you can. See if you can talk it through with someone you're sitting next to, and see if you can get the formulas typed out and plugged in. And then we'll check it. Okay, so for part B is going to look like this. Since this is quarterly, n is now 4. I can just go and actually just highlight that, press enter, and then I'll go in and change all my 1s to 4s, make it a little bit quicker. So there we go, there's a formula, let's press enter. So what's happened here is we're taking the interest that was earned at the end of 1 quarter. So that would only be like a few cents. And then we're timesing that or compounding it 4 times. So really, it's not like you're taking the entire $4,000 and applying it to how much you're compounding. You're only taking the amount you earn in a very small time period and compounding that on top. So that's why this 4,364, it's not much bigger than 4,360. So this is $4,364.82. C is going to look like this. So B was n equals 4. C is going to be n equals 12. We go just highlight that, change the 4s to 12s, make that a 2, and then second delete. Well, let me insert something. There we go. There we go, $4,365.74. And then finally, we have compounding daily. We got to change the 12 to 365. So $4,366.19. So as you can see, now you know if you go to a bank and they say, well, hey, we'll take your money and we'll compound it daily. Does compounding really affect your money in growth? No, not a lot. What affects your growth the most, how much your money is going to increase in value, it's the rate. The rate is the most important. Now you can see 2.92%, not a huge rate. So that's why the more times we compound that small rate, the rate that it increases, the more you compound actually decreases over time. It's kind of hard to think about. We'll talk about it more when I come back. But anyway, those are your two formulas. Remember, compounding interest, that's when you're talking about investing money. Any other scenario that's not talking about investing money, like putting money in a bank, that's going to be your exponential growth and decay. Hope you're able to follow along. I'll see you next time.